This beta attenuation air monitor works because beta particles attenuate when passing through physical matter. The clever bit here is weighing airborne dust using high-speed electrons. Instead of relying on fragile mechanical laboratory scales, continuous environmental monitoring stations measure airborne particulate mass accumulation electronically. Ambient outdoor air enters continuously through a calibrated size-selective intake head designed to separate microscopic particular pollution. These invisible dust particles collect continuously onto a moving ribbon of specialized clean filter tape inside the monitoring instrument. However, attempting to measure raw particulate mass directly on an active filter ribbon introduces an immediate and troublesome engineering flaw that corrupts readings. Clean filter tape is not completely uniform across its entire physical length, displaying subtle microscopic variations in thickness and material density along the roll. If an instrument simply measures beta particle absorption passing through loaded filter paper, natural paper thickness variations distort the final mass calculation. A slightly denser patch of clean filter paper absorbs additional beta particles, falsely appearing to the detector as heavy atmospheric particular pollution. Furthermore, outdoor environmental temperature changes and humidity shifts cause the baseline paper tape media to absorb moisture and expand over time. This structural unpredictability introduces an unacceptable baseline error long before any atmospheric particulate mass is even deposited onto the continuous filter tape. Engineers resolve this filter paper variance by implementing an automated differential baseline measurement prior to every single ambient sampling cycle. Before drawing outdoor air, the instrument measures beta particle transmission through the exact spot of clean filter tape selected for upcoming sampling. This initial electron count establishes a precise reference baseline that accounts for the specific physical thickness and density of that exact tape spot. Only after this clean reference baseline count is stored in internal memory does the sampling pump activate to draw ambient outdoor air through. Once the active sampling interval concludes, the instrument remeasures beta particle attenuation at that exact same spot on the filter media ribbon. Subtracting the initial baseline count isolates the particulate mass, successfully cancelling out any underlying variations in filter paper thickness and humidity. The bigger problem was converting a simple reduction in detected beta particles into a precise standardized ambient air concentration value. Air sample volume varies continuously with atmospheric pressure shifts, ambient outdoor temperature changes, and vacuum pump flow rate fluctuations during collection.
Without precisely controlling and tracking total volumetric flow, knowing the physical mass of collected particulate matter alone cannot yield true concentration figures. Furthermore, beta attenuation physics relies on nuclear emission sources, demanding strictly sealed, factory-regulated, and completely safe industrial monitoring instrumentation. The internal radioisotope emission source must remain permanently enclosed inside factory-calibrated metal shielding to guarantee absolute safety during continuous field operation. Calculating accurate real-time air quality requires seamlessly combining differential nuclear attenuation physics with tightly regulated volumetric airflow tracking systems. The complete monitoring sequence begins outside, where ambient outdoor air is drawn into a calibrated size-selective sampling inlet mounted high atop the monitoring shelter. This inlet uses carefully controlled air intake velocity and inertial separation to remove large debris, while allowing respirable particles under 10 micrometers to pass. A precision vacuum pump located downstream draws the air sample through a temperature-regulated sampling tube at a constant-controlled volumetric flow rate. As the continuous airstream passes through the stationary filter tape, airborne particles accumulate uniformly across a designated circular sample spot. Positioned directly above the filter tape spot is a small factory-sealed radioisotope source that continuously emits high-energy beta particles downward. Beta particles are fast-moving electrons ejected during natural radioisotope decay, possessing sufficient kinetic energy to penetrate thin layers of solid matter. As these fast electrons travel through the filter media and accumulated dust layer, they lose energy through electromagnetic interactions with atomic electrons. This attenuation phenomenon follows a fundamental physics law where beta particle transmission decreases exponentially with increasing total mass per unit area. Crucially, beta particle absorption is determined almost entirely by total electron mass in the beam path, completely independent of chemical elemental composition. Whether the collected dust consists of dark carbon soot, pale mineral soil, or liquid sulfate droplets, equal mass attenuates beta particles identically. A high-sensitivity scintillation counter, or semiconductor detector, positioned directly below the filter tape counts the surviving beta particles passing through.
By comparing the post-sampling beta count to the initial clean baseline count, the onboard microprocessor calculates the exact accumulated particulate mass. Simultaneously, mass flow controllers and temperature sensors integrate the precise volume of air drawn through the filter during the active sampling period. Dividing the calculated particulate mass by the total sampled air volume yields an accurate mass concentration reading in micrograms per cubic meter.
Upon completing the calculation, an automated mechanical reel mechanism advances the continuous filter tape to present a fresh, unexposed spot. This automated tape advancement prevents filter clogging and enables continuous, long-term environmental monitoring without requiring frequent manual technician intervention. Because these monitors are sealed, regulated industrial instruments, internal radiation components are safely contained and protected from unauthorized handling or modification. Data collected by ambient monitoring networks serves environmental regulatory reporting and public forecasting, rather than providing individual personal medical diagnoses. By pairing baseline subtracted beta attenuation physics with precise volumetric air regulation, automated monitoring stations measure invisible airborne dust continuously. This clever combination eliminates filter tape inconsistencies and particle composition biases without relying on fragile physical laboratory balances in field conditions. Factory-sealed beta attenuation monitors remain essential tools across global environmental networks, reliably safeguarding public health through accurate air quality tracking. Understanding how subatomic particle attenuation directly measures particulate mass reveals the sophisticated nuclear engineering powering modern clean air protection systems.